All right, and welcome back to the second video on relational learning, where we'll be giving you a little peek under the hood of how the algorithm works. Now, let me start by telling you that relational learning is hard. There are a lot of challenges involved. First of all, relations can change over time. And second, the amount of relations that you need to learn scales quadratically. I mean, think about it. If you have to learn relations between 5 parameters, you have to learn the relation between the first and the second, the first and the third parameter, the first and the fourth, the first and the fifth. And then between the second and the first, the second and the third, the second and the fourth, and so forth. So you kind of need to learn the number of parameters squared relations. Now, if you're dealing with a network that has millions of parameters, you can imagine that the amount of relations that you need to learn is enormous, right? That's also the reason that we're not doing this on your system. We're doing this in the cloud. Now, even if we do it on the cloud, there are still a lot of challenges. And that's why I'm saying relational learning is hard. That's why Skyline participated in a government-funded research project called the Conscious Project. And here we've been collaborating with universities such as the KU Leuven, the University of Antwerp, but also major industrial partners such as Duracell, the battery company, Engie, the energy company, to tackle these challenges together. So all of the research that I will be talking about was developed together with these partners. Now, okay, in order to just simply give you an intuition about how we do relational learning, I'm going to kick you off with a question. And the question is this: assume that you see the following 4 parameters. Which of these do you think are related to each other? Yeah, just take a quick look. All right. Before I'm going to give you the answer, I'm going to tell you that it's not parameter A and parameter B necessarily. That's what most people will think, and that's what most people would say. Now, why not? Well, the thing is that parameter A and parameter B have a nice periodic behavior, and they look very much alike. But in the end, a lot of parameters have a very nice periodic behavior. Think about the temperature. It goes up during the day and then down during the night. Think about the electricity usage. It goes up during the day and down during the night. Think about the internet usage. Same thing. So a lot of parameters that look the same are actually not at all related to each other. Instead of looking at this purely similar behavior, instead what we do is we're going to look at the places where the parameter suddenly behaves differently. And that leads me to the answer on this question. Which of the following parameters are related? Well, we can't be sure, but we argue that B, C, and D are related. And why? Well, notice that B and D, for example, have odd behaviors at the same points in time. Here, parameter B drops while parameter D has this weird increase. And here, parameter B drops and D drops as well. The same thing for parameter C. It also has weird behaviors at the same timestamps that the other parameters B and D have weird behaviors. So this is what we're going to focus on to learn relations. We're going to check out when parameters are behaving strangely, and parameters that are behaving strangely are likely to be related. Okay, and this intuition is mentioned here again. Now, what do we mean with behaving strangely? Well, we have an anomaly detection algorithm that Tobe has been talking about in this course. So we can say that when a parameter changes behavior, that's a case where we talk about strange behavior. We can also talk about alarms. We can say that parameters are related to each other if their alarms coincide, right? Now, okay, that's a very simple intuition, but how do we do this mathematically? Well, translating this intuition to an algorithm is tricky, but it's very easy to explain the higher steps, right? In order to explain that, let me talk about 2 new concepts, support and frequency. We have 2 parameters here, A and B, and the time axis here. And here I'm telling you when these parameters were in alarm. Now, the support of a parameter is the total number of alarms on that parameter. This means that the support of A equals 3 and the support of B equals 6 because there are 6 alarms on B. The frequency AB is the number of times that A and B have simultaneous alarms. Now, you can imagine that related parameters don't always have alarms that perfectly coincide. It's likely that there's an alarm on A and then an alarm on B 5 minutes later or something like that. So that's why we introduce a window. And I've drawn some of these windows here in red. Now, we're going to say that the alarms on A and B coincide if they have alarms in the same time window. And here I took a time window of, say, 1 hour long. So, okay, what's the frequency of A and B? Well, the frequency of A and B is 2. Why? Well, there are 2 cases where this rectangle contains an alarm of both A and B. There are 2 timestamps where A and B are both in alarm. Okay. Now, how do we define the relation then? Well, we define the relation between A and B as the frequency divided by the support. Said differently, it's the amount of alarms on A that coincide with an alarm on B divided by the total number of alarms on A. In this case, we see that 2 out of 3 alarms on A coincide with an alarm on B, and so we say that the relation strength is 0.666. Note that by definition, the relation strength is always a number between 0 and 1. All right, and that's the simple intuition behind this algorithm. But as I mentioned several times, the reality is a lot more tricky because of various reasons. For example, the scale, how do you make sure that you do all of this very efficiently? The fact that relations can change over time, and so forth and so forth. All right, now that you know about the algorithm, let me talk a little bit about the computational resources. First of all, as I've mentioned, this algorithm is run in the cloud. In fact, why? Well, because you have trillions of relations to learn and you don't want to do that on your system. In order to run it, just make sure you have a cloud subscription, install the modal host and the cloud feed, and you're in business. What about computational resources? Well, the computational resources, are kept low by not updating the relations in real time, but by updating them on a weekly basis. This way, we avoid that we constantly have to do calculations. Now, instead, we just do it once per week. What about storage? Well, for every parameter, we need the support in memory. So this is something that we store in the cloud. For each parameter A, we also need to know how many of its alarms coincided with alarms on B, C, D, E, and so forth. So for each parameter A, we also store a number, frequency AB, where B is any other parameter. Okay, so as you can imagine, this is becoming more and more memory. Now, storage prices are reasonably cheap, fortunately, and we only need to fetch this data once per week, so that way we're able to keep the cost of this rather low. By the way, Skyline is currently covering all of these costs. Now, the next thing, to avoid having too much computational resources, we also do some smart memory reduction techniques. For example, we don't take into account warning alarms. We also don't take into account parameters that did not have an alarm in the past or that had more than 100 alarms in the past, because probably those alarms are rather noisy and are maybe a result of an ill-configured alarm template. Okay, those are the resources on the cloud. What are the resources on your system? Well, in order for you to be able to use the relations, we need to store them on your systems. That's why we do not store all the relations. We only store relations which have a strength higher than 0.5. If you want to know how much memory your relation learning is taking on your system, all you have to do is check out the RAM memory of the model host process. This perfectly reflects how much memory relation learning is using. All right, I guess that covers everything that I wanted to say. Thank you much for your attention. Thank you very much. And we'll be talking about one of the applications of relational learning next week. See you then.